So let's define nxn to be the number fields k of degree n whose Galois closure is Sn and discriminant is less than x. Okay. So we have Marley's conjecture, which sort of gives you a very specific asymptotics for nxn. It actually gives you asymptotic for any specific Galois group sitting inside Sn, but we'll just limit ourselves to Sn. And it says that asymptotically nxn should be some Cn times x. The Cn is quite explicit, but we won't bother with that today. So the progress on this so far is n equal to 3 was proven by Davenport and Helbron. N equal to 4 was settled by Bhargava, and n equal to 5 was settled by Bhargava again. In general, there are a few, beyond this there is no progress, and in general there are a few main difficulties that come up in approaching this problem. The first difficulty that comes up are getting a nice perfect parameterization theorem. So for example, in the case of n equal to 3, this was done by Levi in Delon-Fadi's book, and then generalized to degenerate cases by Gans, Gross, and Savin. So what this particular theorem does is, to every cubic ring, it associates a unique binary cubic form and shows that basically cubic rings are in one-to-one bijection with GL to Z orbits of binary cubic forms. And for n equal to 4 and 5, we have the very cool Bhargava's parameterization of quartic and quintic rings. And similarly, the second problem that comes up is sieving. So once you have a nice parameterization theorem for rings, you sort of sieve out the elements that you are not interested in. And so for n equal to 3, this was actually done by Davenport and Heilbronn. And for n equal to 4, this was done by Bhargava. 4 and 5, this is done by Bhargava. Okay. So in general, even lower bounds on nxn is quite a new phenomenon. And so we have this lower bound, which was done in 2019 on Archive and 2022 in Inventiones, where Bhargava, Shankar, and Wang show that nxn is actually greater than x to the half plus 1 over n. We'll call this result A. And similarly, in 2022 on Archive, they show that nxn is greater than x to the half plus 1 over n minus 1. Okay. Let's call this result B. Okay. So let's understand the structure of result A and B. So result A is connected to monogenic rings. So what is a monogenic ring? A monogenic ring is a ring isomorphic to Z of alpha. Right? So once we have a structure of this type, it gives you a lot of innate information. For example, to a monogenic ring, you have an associated monic polynomial. Right? You have a nice basis for Z of alpha, and you know that the discriminant of Z of alpha is just the discriminant of the monic polynomial. Right? And you know that f of x and f of x plus L will give you the same ring, because Z of alpha is just Z of alpha minus L. So result A is actually based on two facts. One is 100% of the translation orbits give you distinct rings. Right? So if you end up counting translation orbits, you should most of the time get distinct rings. And the second or the major part of the paper was about sieving out the unwanted elements in the parameter space, which in this case is a set of monic polynomials. So these include polynomials which don't correspond to full rings of integers, polynomials whose Galois group may not be Sn, reducible polynomials, etc. Let's analyze result B. So for result B, the parameterization used is known as binary rings. So let f of x comma y denote a binary form, right, with integer quotients. And for simplicity, let's assume a n not equal to 0, and let delta denote the image of x in the algebra, q of x modeled by f x comma 1, basically the field generated by f. Okay. So we define Rf to be the z span of 1 an delta square plus an minus 1 delta, and so on. So we can actually, what happens is this Rf turns out to be a ring, and we can easily see that this ring's discriminant is actually the discriminant of the binary form. So what you get is, we say Rf is the binary ring associated to f, right? So you have a nice association of binary rings to binary form, which sort of allows us to move the counting from rings to very explicit arithmetic objects. Okay? and you have that f and twist of f by some g in GLN2 give you actually the same ring. So you actually would have to count the orbits of GL2 to get rings. So result B is based on the fact that you can sort of find a cone where eventually no two forms correspond to the same ring. You can sort of find a cone. So in that, and basically the difficult part is sieving out the unwanted elements in the parameter space. Okay. So these results are sort of best you can do with those parameterizations. So heuristically, we expect the number of number fields whose ring of integers is monogenic to be about O of x to the half plus 1 over n. Okay. Similarly, we also expect the number of number fields whose ring of integers is binary to again be about this order. So in some sense, to get a better lower bound, we have to get some better parameterizations or more general parameterizations. So to this end, we come to weakly divisible polynomials. The concept of weakly divisible polynomial was actually defined in the previous two papers that we mentioned. So let f of x be a polynomial of degree n. We say f of x is weakly divisible by m at L if m square divides f of L and m divides f prime of L. So actually these polynomials are introduced in those papers as, so if you look at the binary ring associated to f, it is actually not maximal. It is not the ring of integers. And most of their paper is actually dedicated to sieving out these types of polynomials in the tail end. So to remove them from the tail end is sort of the biggest issue. And so we define L is any integer. So we define R prime of f comma m to be the same basis except for the last term, which we divide by m. Right? Now, as it turns out, you can expect, you know what you can expect next. If f is weakly divisible by m at 0, then R prime f comma m is a ring, right? And its discriminant is obviously discriminant of f over m squared. So this gives you a nice new parameterization of rings, using which we can show that the number of rings of rank n with discriminant less than or equal to x is x to the half plus 1 over n minus 4 by 3 plus this small quantity. I think the previous sort of never really put in literature bound was half plus 1 over n minus 1. Okay. And using the tail end estimates in the Bhargava-Shankar-Wang's papers, the second paper, result B paper, we show that nxn is actually a little bit larger than the previous one. So for odd n, we get an improvement of about 1 over 5 n to the 5. And for even n, we get an improvement of about 1 over 88 n to the 10. Right? So an interesting consequence of this is it shows that there exist infinitely many number fields with no small generators using Waller and Widmer's result. So future improvements. So let's see how heuristically how far can this parameterization take us. So obviously this is my next project where the setup in the Bhargava-Shankar-Wang's papers can be better adapted to get tail end estimates more suited to this parameterization. We use the tail estimates as they are currently. So in that case, we expect to get x to the half plus 1 over n minus 1.33. Right? And if we have a conjecture on injectivity, basically which rings will correspond to distinct rings, and under that conjecture, we expect to go as far as x to the half plus 1 over n minus 1.5. And finally, under what I like to call a modular arithmetic equidistribution, we expect to get a lower bound of as good as x to the half plus 1 over n minus 2. I do not think this parameterization can take you beyond this. So the need for more general parameterizations is still there because the lower bound we expect is about x to the 1. Thank you.